Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll learn how to solve a linear system of equations, which is something you actually already know, but we'll learn a better and more simplified method of doing it. So first, let's look at what a linear system of equations is. It is, for example, a system of the form x plus 2y plus 7z is equal to 4 is equal to 9 and 3x minus 2y plus z is equal to 15. We've all seen equations like these before, and sometimes they might not end up having solutions, but generally if you have 3 equations and 3 unknowns, you're going to get one standard set of solutions, that is x is equal to a particular value, y is equal to, and z is equal to. Right, and how do you solve this system of equations? There are many methods. The one I generally prefer is either substitution or eliminating a coefficient. For example, you could multiply this whole row by 2 and then subtract it from the first row, and 2x and 2x will cancel, right? And you'll have one equation in 2 variables y and z. You could do the same thing, multiply this by 3, subtract it from this, you'll get another equation in y and z, and now you have 2 equations in 2 variables. Or you could just write x is equal to 4 minus 2y minus 7z. From the first equation, you could substitute that into the other two, and you get 2 linear equations in 2 variables. Right? So there are many ways of solving this, and you've already solved this before, but now we'll see a much more simplified and systematic method for solving this, and that will not only take care of an equal number of equations and unknowns. Here we have 3 equations and 3 variables, but if we have more equations than unknowns, or if we have less equations than unknowns, then what would happen? That is also something we would know. Excuse me. For example, if you only had 2 equations, the first 2, you did not have the third equation, then you could not get a set of solutions. You would actually have infinite solutions which would have some relations between the two, because you only have 2 equations and 3 unknowns. So fixing x and y, you could calculate the value of z. Sorry, fixing x, you could calculate the value of y and z. Right. What if you had these 3 equations, but you also had a 4th equation, 2x minus 2y plus 7z is equal to 9? It's possible the solution for the first 3 equations will not satisfy the 4th equation, so then you would get no solution at all. Or if the 4th equation was a multiple of the 3rd equation, say, then you would still get one set of solutions despite having 4 equations, because there would really be 3 independent equations. So you have many cases, and the method you use right now, with that method you can only tell which case it is after explicitly calculating the solution. But using what we've learned already, that is matrices, we'll actually devise a systematic approach to solve these. So the first step is to learn how to write a linear system of equations in terms of matrices. By the way, the word linear is used because we all have x, y and z. There is no x square, there is no x into y, there are no terms like that. Every term has one power in x, y or z. Right. So we'll write this in terms of a matrix equation A x is equal to b. Remember, small letters for scalars, small letters with arrow for vectors, capital letters for matrices. That is our notation in this course. Now this would be the same as this system if we chose A is equal to 1, 2, 7, 2 minus 1, 3, 3 minus 2, 1, and we chose B is equal to 4, 9, 15, and we chose X is equal to X, Y, Z. Actually, let me just use small a here, because x might end up being resulting in a confusion, right? So you take this matrix, multiply by this matrix, right? What do you get? You get 1, 2, 7, 2 minus 1, 3, 3 minus 2, 1. You multiply it by x, y, z. You get a 3 cross 1 matrix with 3 terms. The first row first column will be first row first column, that is this multiplied by this. Now for the first time now we are multiplying a variable instead of two rows full of numbers, but that's fine, that doesn't make a difference. So it will be x plus 2y plus 7z, then 2x minus y plus 3z, that will be the second row. And if that is equal to the vector 4, 9, 15, then the first row x plus 2y plus 7z has to be equal to 4. The second row 2x minus y plus 3z has to be equal to 9, and so on. So we see how this big set of three equations can actually be represented by one single equation where a and b are column vectors. A is the vector of variables, b is the vector of the RHS constants, and a is called the coefficient matrix. Because it has the coefficients of x, y and z in that exact order, right? So now x, y and z are just the variables. You could call them x, y, z or x1, x2, x3 or a, b, c or u, v, w. It wouldn't matter. Those are just the variables, and their values are determined by the matrix A and the vector B, right? So we create from this linear system of equations something called an augmented matrix. In which we actually add one more column to the coefficient matrix, and that column is the vector b. So here the augmented matrix would be, I'm sorry, I forgot what the numbers were, something like 2 minus 1 3 2 0 1. I just make the numbers again, I'm sorry, 4 6 9. Let's say this was a, and then you had b, which was 4 9 and 13. So you just put a line here and you say 4 9 and 13. So basically this whole thing was the matrix A and this was the vector B, and you add them together and this is referred to as A tilde or the augmented matrix. Now why do we make this augmented matrix? Because this augmented matrix completely determines the system. Basically two things were determining the system, A and B, the matrix A and the column vector B. So we decided instead of two things contributing to the value of the variables, we'll just join them together so that we have all the numbers we need in one matrix called the augmented matrix, and this matrix completely determines the system. If you had a different matrix, that would correspond to a different set of linear equations along with the b's on the right side, and it would give you a different set of solutions. Right, so now let's go back and do it in a little bit more rigorous detail, and we'll take a standard set of m equations in n variables. So they could be different, and now we'll consider the general case as well. So the system would be something like a11 x1 plus a12 x2 plus a13 x3 plus a1n xn is equal to b1. So this would be the first equation. No x square, no x1, x2, because then it would not be a linear system of equations, and we would not be able to represent it by a matrix. The second equation would be something like a21 x1 plus a22 x2 plus a2n xn is equal to b2. Now you would have many equations like this. The last equation would be a m1 x1, because we have m equations, plus a m2 x2 plus a mn xn is equal to b m. Now this system of equations can easily be represented by a x is equal to b, with a is equal to a11 a12, or the standard a which we use, am1 amn. This would be a. X would be x1 x2 till xm, and b would be sorry, this should be till xn, b1, b2 till bn. So this is an m cross n matrix multiplied by an n cross 1 matrix gives us an m cross 1 matrix. Right. Now you can easily see that this row multiplied by this column a11x1, a12x2, that has to be equal to b1. So this equation indeed does represent this particular linear system of equations. Right. Now the augmented matrix will just be this matrix with an extra column here, so it will be m cross n plus 1, one extra column, and that column will be b1, b2 till bn. Right. By the way, if b is equal to 0, which means b1 is equal to b2 is equal to dot 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 is equal to bm is equal to 0, then the system of equations is called homogeneous. And a homogeneous system of equations always has at least a trivial solution, which is that x is equal to 0. So if the RHS is 0 everywhere and all x's are 0, x1, x2 till xn, then obviously you would have 0 equal to 0 in every equation, which would be valid. So a homogeneous system of equations, meaning all the right hand sides are 0 or b is 0, always have the trivial solution x is equal to 0. It may also have non-trivial solution. Right now we are looking at a standard non-homogeneous case. So let's look at the augmented matrix for a second now. Augmented matrix A tilde will be till a1n, a21, am1 till amn, and then you'll have another row b1, b2 till bn. This is an augmented matrix. Now this corresponds to one linear system of equations, the one which I wrote previously, a11x1 plus a12x2 and so on. What if we had another augmented matrix, let's say a1 tilde, which would be almost the same as the first matrix, this augmented matrix, except the first two rows would be interchanged. So we would have a21, a22 till a2n, and you would have b2, a11, a12 till a1n, b1, and the rest of them would be the same till am1, amn, bn. Right, so this is the first augmented matrix with the first two rows interchanged. What linear system does this correspond to? It corresponds to pretty much the same linear system, except the first equation and the second equation have been interchanged. But we know that does not change the solution. So this augmented matrix has the same set of solutions. So this was my purpose here to show you that you could obviously you could interchange two equations. The second equation you can write up and the first equation you can write down. That wouldn't make a difference at all. Similarly, you can interchange two rows and that would not change the set of solutions. Right. Now let's say you have 2x plus y is equal to 7 and x minus y is equal to 5. Now what if you add the two equations? Then you would get some, let's take this to be 3y, just for the sake of it. What if you add the two equations? You'll get 3x minus 2y is equal to 12. Right. Now what if you replace the second equation with this? You know, since this equation came from the first equation, it will still have the same set of solutions. So if you replace the second equation by say second row by say 2 times the second row plus row 5, that would still give the same set of solutions. It would give a new augmented matrix, but the same set of solutions, because the equations would just have been manipulated. What if you replace the last row by the sum of the last and the second last row? That would still keep the same set of solutions, because that would correspond to just replacing the last equation by the sum of the last and the second last equation, which are the sort of manipulations you do anyway to try to get the solution. Right. So you can actually manipulate these augmented matrices. You can do certain things on the augmented matrices which are called elementary row operations. or EROs. And elementary row operations are those operations which you can do on the augmented matrix which don't change the solution set. You cannot, for example, multiply this entry by 7, because that would change the set of equations, and that would give a different set of solutions. But what if you multiply every entry in this row by 7? That would not change the set of solutions, because it would be equivalent to multiplying an equation on both sides by 7. Right? So multiplying just this entry by 7 would not constitute an elementary row operation, but multiplying this whole row by 7 would constitute an elementary row operation. So you can do elementary row operations to simplify an augmented matrix into a form which we can actually solve later. So let's look at what elementary row operations are actually valid. So I'll first write what these row operations correspond to for matrices, and I'll write the equivalent in terms of the equations. Because if I hadn't taught you this, which you didn't know before this video, you still knew how to solve a linear system of equations by adding equations together, by multiplying an equation on both sides by a certain number and manipulating them to get simplified results. So the first ERO for matrices is interchange of two rows. And that is equivalent to an interchange of two equations, which we know does not alter the solution set. The second ERO is, now keep in mind this is for rows, you cannot interchange two columns. Try it at home and you'll see that will give you a new linear system of equations which would have a different set of solutions. Multiplication of a row by a non-zero constant. This does not change the solution set, because this is just like multiplication of an equation by a non-zero constant. And the third is addition of a constant multiple of one row to another. And that corresponds to, you guessed it, addition of a constant multiple of one equation. To each other. Right? Now doing this, you can actually get a new linear system of equations. So let's say initially you had a linear system of equations S1 and you did EROs on it and you got it to S2. S2 and S1 are said to be row equivalent if you can get S2 from S1 by finitely many elementary row operations. Right? So obviously the rule is row equivalent linear systems have the same set of solutions. Right? You could interchange two rows, you could multiply a row by 7 on each side. All of that would give you, technically would give you a new linear system of equations S2, but since they would be row equivalent, that is, you can get 1 from 2 by finitely many row operations, elementary row operations, they would have the same set of solutions. Right? So how would this occur? So let's just say you have an augmented matrix 2 1 6 4 3 1 9 2 6 1 3 7. Right. This augmented matrix A tilde would correspond to 2x plus y plus 6z is equal to 4, 3x plus y plus 9z is equal to 2, 6x plus y plus 3z is equal to 7. This would correspond to this. Now what you do is you keep doing elementary row operations on this to get it into something we call a row echelon form. We'll discuss this in a second, but it basically is a way to get this into a simplified manner. A row echelon form is an augmented matrix of the form of, if this is a 3 cross 4 matrix, it would be of the form of alpha, beta, gamma, delta. I don't know a lot of Greek symbols. I'll just write A, B, C, B, D, E, F. 0, 0, 0, 0, 0, 0. Basically, these terms, the lower triangle would be 0. A row echelon form is basically an upper triangular matrix, right? So you reduce this to an upper triangular matrix by doing row operations. So I'll not do the whole process. I'll just show you how it might be done. So let's say you wanted to make this term a 0 first. So you could add to it minus 2 times the second equation. So you say row 3 goes to row 3 plus minus 2 times row 2. This is an elementary row operation because it falls into the category of operations we saw just a moment ago, right? So if you do this, then the augmented matrix would become 2, 1, 6, 4, 3, 1, 9, 2, and this would be row 3 plus minus 2 times this. So this would be 0, this would be minus 1, this would be 3 minus 18, that is minus 15, and this would be 7 minus 4, that is 3. This is the same as you multiply this by 2, by minus 2, and you add it to this, right? Now you remove this thing. Now you can add these two terms, right? Row 3 goes to row 3 plus row 2. Right, actually that would be a bad move because you'll get 3 again here. But now you can do this next step. You can multiply this equation by 2 and this by minus 3 and add them up and make it this equation. So then you'll get 0 here as well. So you get 0 in these two places. Once you get 0 in these two places, you add them up correspondingly to get this a 0. Right, and you keep doing these things until you get this row echelon form. Right, what is the benefit of the row echelon form? So let's say now you have reduced the augmented matrix into the row echelon form. So let's say you have A, B, C, D, E, F, G, H, I, right, J. Actually, let's take this to be 0. I'll explain that in a second too. So let's say you have this, right. So what is this an example of? This is AX plus BY plus CZ is equal to D. EY plus FZ is equal to G, HZ is equal to I. Right, we've made all these terms 0. Now you can solve this system of equations by what is called back substitution, which is quite easy. From this you get Z is equal to I by H. You input Z here, you'll get the value of Y. Put Z and Y here and you'll get the value of X. Right, so earlier we had X and X term here and X and Y term here as well, and we just manipulated to make those terms 0. We got this, which was basically the row echelon form, and we went back to do it to get the solution by back substitution. Right, so now let's do this in the most generic form. I'm going to take the most generic m cross n equations which we took earlier, and I'm going to show you how the row echelon form might look and what different cases of row echelon form mean. So eventually the row echelon form will look to you to be something like this. A11, A12. These, by the way, are different coefficients. These are not the original one. Now we got this in a row echelon form, and these are the coefficients. So here, let's say you have B1, B2, dot dot dot. So this will go to A1n. Then you'll have, I've already used B here, so let's go from A to C. You'll have C22 going to C2n. Then you'll have D33 going to D3n, and so on. Right. These terms, let's say you have it unto KRR dot KRN, and this goes till BR, and you have all these terms being 0, right? And you have all these terms being 0, right? Now if it were indeed a square matrix, then if it were indeed the number of equations would have been equal to the number of unknowns, then this would be just one term like we got previously, and we could easily back substitute it. But for the sake of it, we'll just dot 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 BM, write it right now, BR plus 1. These are the other terms. This is the most generic row echelon form you could ever get, right? Now there are three possible cases which tell you the three different types of solutions. The first one is if R is equal to N. Now this term is KRR, this term is KRN. R is equal to N means this is just one term, right? That means you've truly gotten a triangular form where this is just one term, something times R is equal to this. If R is equal to N and BR plus 1 is equal to BR plus 2 is equal to dot 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 BM is equal to 0. That means if this is just one term and all these terms are 0, that is the best possible case, and that is the case when you have exactly one solution. Right, because these terms will be 0, so you'll have 0 equal to 0, which is consistent. This will be KRR, so you'll get this variable directly, and you can get the others by back substitution. Right. The second case, if R is less than N, that means you actually have 2 or 3 terms here, right? If R is less than N and BR plus 1 is equal to BR plus 2 is equal to dot 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 BM is equal to 0. These terms are 0, but this is not just one term, these are like 3 terms. Then you have infinite solutions. I hope this is becoming clearer to you now. Right, the first case would be of the form of, this would be our augmented matrix, 1, 2, 3, 4, 3, 6, 4, 7, 9. Right. Yeah. This would be the first case where you only have one entry here. So you'll have 7z is equal to 9. So z is equal to 9 by 7. Put it here, you get this. Put it here, you get this. This would be the first case. The second case would be, for example, 1, 2, 3, 4, 3, 6, 4, and everything else would be 0. Then you would have the smallest equation being this, which would be 3y plus 6z is equal to 4. Right. So now you have infinite solutions because you have more equations than unknowns. Sorry, more unknowns than equations. Right. And the third case, if either one of BR plus 1, BR plus 2, BM is 0, then you have is non-zero, then you have no solution. Now this might seem a lot to learn in one video, but you think about this, we are just paralleling all the knowledge you have of solving linear systems already. If you have this sort of equation, then you'll have 0 into x is equal to something non-zero, which is not possible. Right? That would be of the sort if you have inconsistent equations. You have 2 unknowns, but you have 3 equations which are not consistent among themselves. So you would have no solution. So again, repeating, this case is the best case where it tapers off to a triangle. You have one entry at the end here apart from the augmented column. That is exactly one solution. You have many entries here, that is infinite solutions, and you actually have some entries non-zero here. In first both A and B, these entries were 0. If any one of these is non-zero, you do not have any solution. Right. So we see that even though this might seem a little bit tiresome at first, I suggest that you try and practice it and you get fluent with it, and we actually see that this is a much more systematic method which actually can tell us exactly how many solutions we are and what kind of system we're dealing with. Right. Thank you.